Okay, so I thought we'd take a moment to walk through just a little bit of additional stuff about numerical integration that maybe has less to do with the algorithm side of things, but maybe deals with how you would actually approach one of these problems if you just were given some ODE that you were trying to solve. So this is going to be more of sort of a pragmatic sense of how should approach ODE problems. And this is highly biased based on my own experience rather than being based off of first principles or whatever. Um, okay, so in my own research, I spent a lot of time doing numerical integration, particularly recently of sort of low-dimensional dynamical systems in continuous time. Just to give an idea of how much time I spent on integration, this is a figure from a paper I wrote last year where I tried to, for a machine learning problem, I tried to create a benchmark containing basically every chaotic dynamical system that I could find in the literature. So this includes familiar systems. So I have the Lorentz attractor, which we saw in class. This also has the Hadley convective cell, which we also used, and some other couple famous ones, like I think that the Rossler attractor is in here somewhere. But basically, this is a giant database of equations. All of these are equations that at some point someone has alleged uh, exhibit some variant of chaos or have a chaotic attractor. So these are dissipative chaotic systems for the most part. Um, so all of these are just equations in some paper from the 80s or something. So I took all these equations, wrote them in Python, and then I wanted to integrate all of them to create all these attractors and use them as sort of a benchmark for a bunch of different time series analysis techniques. And one of the first things that you run into when dealing with all of these different systems is that it's actually pretty hard to replicate the chaotic dynamics that are claimed across a bunch of different papers because the properties of chaotic systems are so dependent on the different time scales present or the different features of the underlying dynamical system. So I spent a lot of time on this problem, but one of the things that really stood out to me is that it turned out that for a lot of these different systems, there were a couple of best practices that were shared across all of them that made it possible to produce a plot like this, where I'm able to integrate all these different systems, observe their chaotic dynamics, and not have to fuss around too much with picking a time step or initial conditions. So this is the kind of problem that I've encountered in real research that maybe bears some relevance to how I might suggest going about solving some generic ODE that you might encounter in real life. Okay, so as we saw in class, and as I would generally recommend if you encounter a problem in research, it's usually a good idea rather than rolling your own implementation of Runyakuda or some algorithm we saw in class, it's usually good to at least start by trying one of these built-in integrators that people use. So I think a lot of people here use either MATLAB or Python. So in Python, we saw in class that there's this built-in integrator called solve IVP, the solve initial value problem, that will take an initial condition, take some time, and roll out a trajectory. There's also an older integrator in Python called ODE_int, which some of you may have used. It does similar things to this, but it has slightly different syntax, and it doesn't have the same breadth of methods that solve IVP has. Um, in MATLAB, I think there's a similar built-in integration routine. I'm not quite as familiar with it. And for those of you who use Fortran or C++ bindings of Fortran, there's LSODA, which is a similar sort of general purpose integrator. And the idea behind these general purpose integrators is that they don't implement a single specific algorithm. So it's not like they just use Runyakuda like we did in class. Rather, they're a wrapper that has a single API, a single syntax where I give it my problem, I give it my specifications, then I can pick my integrator, and then it'll use that to solve the problem. So it basically hides all that sort of boilerplate code. And the only thing I have to swap out is the actual algorithm I'm using to integrate. So by default, a lot of these integrators use a fixed step method, like Runyakuda is probably the most common. Sometimes you'll also see Dormand prints as the default method. I think this is true in newer versions of Python as well as in MATLAB. Um, so both Runyakuda and Dormand prints are explicit. However, Dormand prints is variable step, which as we saw in class can come in very handy for elaborate problems. Another method that comes up a lot is LSODA. So LSODA is actually the name, I believe, of a Fortran routine originally. And it basically is an integrator. It's highly optimized, it's compiled, et cetera, et cetera. But basically, it adaptively switches integrating between Adams Bashforth, which is a multi-step method that we saw in class, and an implicit routine based off of whether the right-hand side is fluctuating quickly. So another way of saying that is that this Lipschitz constant, which basically tells you how stiff your problem is, if it detects that that's a really big number, it'll try to switch to an integrator that's more appropriate for stiff problems. So there's a ton of integrators that are sort of built in to solve IVP and its relatives in other languages. One that I find myself using a lot is actually this Redao method for that image I showed before of all these different chaotic attractors. Redao ended up being one of the better methods. It was very consistent across these different methods, and it had nice properties. Like if I changed the initial time step, the attractor wouldn't change. So it was very good at guessing the right time steps. So generally, I found Redao very useful for low-dimensional chaotic systems. But as with everything, picking your integrator is a function of how expensive your right-hand side is to call, how stiff your problem is, and then whether the structure of the implicit problem is ill-posed or not, which can make it difficult to use an implicit integrator. Okay, so my general rule of thumb, if you encounter some ODE in the wild that you need to generate a trajectory from, is that you should always start with solve IVP before you try to build some custom integrator for it, because usually there's enough to do just trying out all these different options for the method and trying time steps and stuff like that. You could also imagine making changes to things like the tolerances and other things that might change the properties. So basically poking around with the API of your built-in integrator will already give you an idea of whether your problem is amenable to using one of these highly optimized internal methods. Generally speaking, to get an idea of your problems, how well behaved it is, I recommend starting with a fixed step integrator like Runyakuda or Dormant Prince, or maybe not fixed step, but explicit step, because that will tell you if you have a nasty problem that's going to require a more elaborate approach. And then if you want to do something like generate a fiducial trajectory, so you want to burn a bunch of compute in order to get a really, really accurate, very, very small maximum step trajectory, I'd recommend doing that with Runyakuda or Dormant Prince, just so you have a sanity check of your later results with a different integrator. But having said that, most of the time, if you have at least two very well separated timescales, so maybe you have a relaxation oscillator where it slowly builds up and suddenly releases, or you have a chaotic system, generally you're going to want to pick a variable step integrator like this Redao method that I find myself using a lot. So that's the first thing you should do is pick your integration scheme, generate fiducial trajectories, and just get a sense of whether this is going to work for you. Then after you do that, you probably want to spend most of your time speeding up the integration so it's easy to roll out additional trajectories. So I'm going to spend a lot of time right now focusing on the different heuristics that you can use to roll out integrations or to speed up computing integrations. So this is the different ways that you could speed up the problem. So the first thing we'll talk about, which we'll see downstream from here, is that if your right-hand side of your equation can be written in a form that's like a matrix vector product, then you should try to make sure you do that using built-ins. That way you're not having a for loop every time your right-hand side is called. Okay, so you should use NumPy best practices to vectorize your right-hand side so you don't have any loops within your call to the function at every time step. Okay, so drop all for loops. The next thing that you want to do is if you have an analytic expression, you might consider going through the trouble of solving for the analytic form of the Jacobian matrix, right? So that's this matrix of partial derivatives of each dynamical variable's time derivative with respect to every dynamical variable. And that's because, as we saw with implicit methods, having the Jacobian is very useful if you want to use an implicit method. I mentioned that some of these built-in methods are implicit or use implicit methods. If you don't give them the right-hand side, they'll try to use finite differences, which, as we know, is extremely inefficient as your dimensionality increases. So maybe in 3 dimensions, like the Lorentz attractor, you can get away with finite differences. But at some point, with a very high dimensional system, it might be nice to pass your integrator an analytic function that computes the Jacobian if you want to use some of these implicit integrators that on some level are trying to invert the right-hand side of some matrix within each call to the right-hand side. The other more practical things I'll talk about today are you could use hardware acceleration to speed up your integration. So this is going to be basically a computer trick that's going to speed up how quickly you call that right-hand side. Uh, the intuition here is that maybe instead of just having Python call that function repeatedly, it would make sense to have parts of that right-hand side be compiled so they run super fast. And hardware acceleration is going to be a trick to do that relatively painlessly. However, if all of this fails, you might have a problem that doesn't lend itself to just throwing it into a built-in solver. So in my experience, when I've had something like an integral differential equation, so that's a differential equation where you have like a non-local term, maybe you have a term that depends on an integral over all past time values, like an impulse response, then you might find that built-in solvers are not going to handle it. So you're going to have to actually explicitly write your own solver. Other cases where that might come up, stochastic, there are some tools out there, but it's not as well tread as deterministic problems. But then delay equations, where like y dot depends on y at t minus tau, those equations are very complicated to work with. And in my experience, there's not really well optimized built-in packages for dealing with them. But that's at least in my personal experience. So for delay equations, you might find yourself rolling your own solution. Okay, so that's a little bit about how you might attack some weird equation that you're given that you're trying to solve. So just to maybe illustrate some of those aspects, here I'm going to use an example problem that corresponds to a reasonably high dimensional system where we can use some of these different tricks to speed it up. So the problem I'm trying to solve is the synchronization of a set of coupled oscillators. So the idea here is that every one of my individuals, so I indexes individual units, each one of these is an oscillator. You can think of it as a pendulum, but we're going to abstract it and say that's something more like an object undergoing a limit cycle continuously. So every variable left to its own devices just wants to go on a limit cycle in phase space at a speed that depends on the specific one. So I have theta I dot equals omega I, where that's the natural frequency that I want to go around. And I could do something like if I had a pendulum, I could map its oscillations to a theta-like variable if I wanted to, but we're just going to keep it generic and assume that the resting state of an individual oscillator is something like going around at a fixed rate that's unique to every oscillator. Okay, so that's a single oscillator. And then with a set of coupled oscillators, I have an interaction term where now my dynamics don't just have this tendency to go around, it also has this funny term where my phase as an individual oscillator is affected by the phases of everyone else. And is affected through the sinusoidal coupling. So you can play around with the different limits of this equation, but the basic idea is that this term, the interaction term, goes to zero when everyone has the same phase, right? Because then all these theta j's minus theta i's go to zero, sine of zero is zero. So then everyone kind of moves together. So if my omega i's were all the same, then that state where everyone moves together would be globally attracting, right? I would always end up in that state where everyone is the same phase, because this is basically just penalizing people for having different phases as they move around the unit circle. So what makes the Kermoto model interesting is that if I have different frequencies, that means that without interactions, different oscillators would want to go around at different speeds. And so there's this competition between the different speeds of the oscillators, which tend to sort of disperse them on the unit circle, and this interaction term where every oscillator is coupled to everyone else. And so they want to sort of join together. So you have this fight between dispersion and synchronization. And I'll just mention that I have global coupling. So I have a single value K that basically says how strong my forcing is here. But you can imagine a more elaborate version of this would look something like a Hopfield model or a spin glass where I have K of ij, so I have individual couplings. So I can make this problem harder if I wanted to. But even the simple version where everyone is all-to-all coupled has interesting properties to it. Mainly this competition between everyone wants to do their own thing, which would occur when K is small, and everyone just joining together and synchronizing when K is large. And I'll mention that this seems like a super idealized model, right? I'm talking about oscillators on circles. But this Kuramoto model is kind of a universal model. So you'll see variants of it that appear in all sorts of weird places. A famous one is gene regulatory networks in cells. They can synchronize together to form things that look like metabolic cycles or even rhythms. Famously, people have used variants of this coupled oscillator equation to describe how groups of fireflies synchronize. They're flashing with each other. The idea being that each firefly might have a slightly different natural frequency, but it observes its neighbors, and so it sort of updates its flashing rate depending on others, instead of getting entire flocks that flash together. Um, and you can even reduce other problems like orbital motion and orbital resonances can have Kuramoto-like properties. So this is a simple equation, but it has kind of a universal structure to it. And it also has a controllable dimensionality where as I add more n, I have more dynamical variables that I have to deal with. Okay, so the Kuramoto model, here's my implementation of it. So my constructor is going to take the number of oscillators, right? It's the individual number of units. K tells me how much they want to synchronize. And then the other parameters I have to initialize before running this is going to be this distribution of natural frequencies, which you recall corresponds to the tendency of this group of oscillators to disperse as opposed to coming together. Because if everyone has very different intrinsic frequencies, it's harder to synchronize. So my constructor basically takes a width parameter, which is like the width of the distribution of frequencies, and it just samples a bunch of random frequencies centered around some mean. So it's parameterizing this model, number of oscillators, K, the coupling among them, and then the individual frequencies of all the oscillators, which I'm just going to randomly sample every time I construct this function. But that distribution has a center and a spread, and the spread is going to be important. Okay, so that's all this is. This is just implementation of this equation. So then actually calling this for the right-hand side just consists of taking all of my phases, finding all of the pairwise differences. So this is a vectorized version of finding theta I minus theta j, and then passing that set of differences. So now it's a matrix that's n by n because it's I as theta I minus theta j for every pair I and j. I pass that to the sine function. Then I have a contraction here, right? I'm summing. So I sum over all the rows and I get a vector out. So the actual sequence of operations here is x is an n length vector. I extrude it to a phase difference matrix, which is n by n. And I then sum to get the net force acting on every individual oscillator. So I contract back down to an n vector, to a length n vector. And so this then encodes sort of the logic of my Kuramoto interaction term. And one thing I just noticed is here, in order to just make this a little bit better behaved, I'm dividing k by n, whereas here I'm just doing a bare sum. So I probably should put a 1 over n here just to make sure that we're consistent across the notebook. Okay. And this just helps us avoid having weird scalings of k with n. Okay, so this should exactly match this logic. Again, I just use some like broadcasting and vectorization tricks to avoid having a for loop over this sum. Okay, so to integrate this, right, I'm just going to choose n, choose k, and then I'm going to choose the average center of my distribution of natural frequencies. This is callable, so I have a call function. So once I initialize this, I can treat it like a function that will just give me the right-hand side. So then I just have to specify initial conditions. So these initial conditions, in my case, are going to be uniformly random across the first half of the unit circle. So like if this is the circle of possible theta values, I'm just picking random values on this top half. I'm going to start out there, and I'm just going to pass all that into solve IVP. So this equation is going to be the right-hand side. So every time I call that, I implicitly am calling the right-hand side. I want to integrate from 0 to 100. My initial conditions are scattered across the half circle. And I've chosen to use Runyakuda just for demonstrative purposes, but I could use a fancier integrator if I wanted to. Okay, so let's see if that runs. Okay, good. So you can see here that these are the phases of all of my individual oscillators as a function of time. And importantly, I haven't constrained them to fall within the interval 0 to pi, right? So I can go around in a circle, and technically I wrap around back to 0 when I cross, but I haven't imposed that constraint. So really I can have my phases just sort of uniformly increase, but implicitly a linear increase in the phase just corresponds to gradually going around this circle at the same speed set by your some natural frequency. So linear increase on the phase plot just corresponds to this case where the oscillator is just doing its thing, moving along the circle. I mentioned this just because like I could have taken a mod function that forces these down to always fall within the 2 pi interval, but that wouldn't do anything interesting. It would just cause this to look like a bunch of zigzags. And it would introduce discontinuities in my trajectories, which are not real. They're just a consequence of the fact that I'm trying to visualize an angular variable on a linear plot. Okay, so you can see from my solution to the Kuromoto model here that in this case, my oscillators did not synchronize, right? So you can see these individual trajectories, they all are sort of going off, but importantly, they're moving at different rates, right? So this line is a higher slope, it crosses that line. So that means that on the unit circle, this blue oscillator actually passed the pink oscillator because it's moving faster. So what that means is that in this case, the first term here, the dispersion, all the oscillators want to go at their own natural speeds. That term won completely. It means that basically this interaction is negligible here. And so all the oscillators are basically decoupled and going around at their own rate. So what I'm going to do is I'm just going to increase K, which is going to increase the relative effect of the second term to see if adding this interaction term that penalizes phase differences gives me qualitatively different dynamics. Okay, so here's my K. So let's just increase that by a factor of 10 to see if that gets me the effect. Okay, cool. So you can see what happened here, right, is that everyone starts out going at their own rate, but they very quickly converge to the same frequency or the same speed at which they're traversing the circle. So instead of having all these different oscillators moving separately, they're now moving together as a pack. And that's because they've been sort of squeezed into the same interval, thanks to this term that causes them to come together. And I can increase K even more to really force that to happen. So one thing that you'll notice is that in this case, not only did the oscillators start moving at the same speed, they also moved to the same angular position. So they all basically collapsed to a single like ensemble of oscillators that's moving together. So I can basically describe the entire system by the mean phase, which is basic because there's basically no dispersion. So as I increase K, I first go to this regime where everyone moves at the same speed. So the system is just co-rotating together, but the positions relative to one another are fixed. So they're phase locked relative to one another. But then as I further increase K, beyond just being phase locked, you get full synchronization where they actually move together. So those are sort of two regimes where, or I guess it's three regimes. The regime where everyone does their own thing, the regime where the forcing is enough to cause everyone to move at the same speed, that's the steady state. And then this regime where K is really strong, where everyone sort of clusters together to the same angle and moves together. And depending on K and your observation time, you'll see those different effects unfold over different time scales in the system. Okay, so that's the Kuromoto model and the kinds of different things that it does as you change K and N, or as you change K. And I should mention, I won't do it here because it's redundant, but I could also change the dispersion. And you can imagine that increasing dispersion would make it harder to reach that synchronized limit. Okay. So in order to call the right-hand side of this equation, I have to do essentially a broadcast followed by a contraction. These are vectorized, but they still are the most expensive steps. So you can probably guess that a large amount of the limitation on how fast I can integrate this has to do with the size of n. Because implicitly, in order to compute this phase difference thing, I have to outer product to a n by n vector, n by n matrix. That takes a lot of memory and as well as a lot of operations to build that matrix. So you can imagine that this method probably has unfavorable scaling with the number of oscillators. So here what I've done is I've just done a timing test where I've tried integrating the pack of oscillators for very small n is 10 here, and then I've repeated the experiment for n equals 100. And you can see that basically the runtime goes up by a factor of roughly 20 or 2000 rather. So, I get basically an order of magnitude increase in the runtime of the integration by going up by an order of magnitude in n. So that's pretty bad because that basically means that I'm paying a penalty proportional to the size of that matrix I have to build to find all the phase differences, right? So as I raised n by a factor of 10, the size of that matrix increases by a factor of 100. So I'm paying a pretty big penalty in order to upscale my Kuramoto term. So that tells me that the limiting time of my integration is going to be tied to the number of oscillators and the need to construct this giant matrix. I'm probably that's probably the variable that I need to pay the most attention to optimizing on. And I'll mention, I didn't include it here because I thought it was a bit of a straw man, that if I really wanted to suffer, I wouldn't have vectorized this. I would have just had a double for loop over I and j. That would have quite literally implemented this logic, but that would have been so slow, it wouldn't even have been worth including here. So vectorizing at least gets us a prefactor speed up, but we still have some intrinsic slowdown due to the fact that the constructing that large n by n matrix is expensive. That's the Kuramoto model. That's some of what it does. And so we're going to try to speed this up using a couple of tricks. Okay. So some of these optimizations aren't mathematical in nature. They're really more sort of computational. They're just tricks that might allow you to take this right-hand side and compute it faster. So I'm working so far exclusively in Python, right? Every step in my workflow has involved calling Python functions, et cetera, et cetera. And so on some level, my slowdown, while some of it's algorithmic in nature, I have to have this n by n matrix, some of it is also just how efficient Python is at creating matrices, doing matrix multiplication, et cetera, et cetera. So the reason that Python, you might hear that it's slow compared to languages like Fortran and C, is that on some level, Python is stuck in that because it doesn't have an explicit compilation step, every time I run it, it has to dynamically figure out what the type of every variable that I've given it is. And it has to do a bunch of work basically to figure out what I'm trying to do, convert it into something that the CPU can understand, and then go from there. So the fact that Python is not a compiled language, it has to dynamically interpret the code I've written in human readable form. It has to convert that to machine code every time I start a process. That is where you're going to get a lot of the overhead that leads to slowdowns versus compiled languages. So there's a couple of things that it's doing every time I run a Python function. The first is that I've never actually told Python that I'm working with floats here or that I'm working with non-integers. So it has to figure that out based off of the context. So it has to do type inference, which takes time. Once it does that type inference, it can then figure out how much memory it needs to set aside for each variable, as well as how long it needs to hold that memory before that variable is no longer used and can get sort of freed up. And so Python has to dynamically decide how to allocate memory and as well as how to free it up. And that collective process in other languages is sort of the garbage collection where you allocate memory and you deallocate it. So it's doing that all implicitly. I'm not telling it how to do that. And so that leads to overhead when it runs the program. That's some of the limitations of Python. Then the other one that you'll frequently hear is called the global interpreter lock. This, I think, is unique to Python and Python-like languages. There might be languages that are interpreted but get around it, but I could be wrong. This might be intrinsic to all interpreted languages. So the idea here is that Python is trying to figure out when a variable appears, what type it is, how much memory to set aside, and then if that variable stops being used at some point, it would like to free up that memory so I don't just have exponentially increasing memory use. So the problem with that is that if I try to, for example, take my interpreter and run it across multiple threads, there could be this weird situation where this thread thinks a variable has been freed up so you can release the memory, but it turns out it actually needs to get used on this thread. And so in other words, there's this lock because the threads can't be decoupled from each other, because even if maybe the program itself can be split into parts, actually figuring out whether memory is available or whether memory can be freed up requires talking across the different parts. So you have the locking here is this idea that on some level, you have like a single effective thread to keep track of all the memory when it's interpreting your program. So this can be a big slowdown of an interpreted language versus something where I've explicitly said, get rid of this memory, et cetera, et cetera. Okay, so that's why Python is slower in principle than C or Fortran or other languages where you actually hit compile before you actually do any running. But rather than just saying that we should give up and use Fortran or whatever your favorite language is, there are some ways around this that use tricks that are sort of collectively known as just-in-time compilation. And the idea is that the interpreter, the first time it runs the code, it can basically build a compilation graph, infer the types, do the memory stuff. And then on sort of future calls to that function, it can use that compiled code. So it's like a secret compilation step where I cache the initial call, and then based off of what I've cached, I use that compiled version uh, to run things faster the next couple of times a function's called. And you could imagine why this would be useful for numerical integration, because I have this right-hand side function that implements all my physics. And I'm going to call that right-hand function a bunch of times. So maybe the first time I compile it, but then the thousands of other iterations, I'm just going to call that compiled version. So just-in-time compilation, we could imagine would be useful for a problem like this one. Okay, so just-in-time compilation is going to be a way to get compiled like speeds in an interpreted language like Python. Okay, so before I get into just-in-time compilation, I just want to mention a little bit about how your computer's memory works, just to give an idea as to why you might run into problems with the speed of integrating large numbers of dynamical variables. So I showed before that you got this really nasty increase of, I think, about 20x in runtime as I raised the number of oscillators by 10x. And so what causes that spike? Some of that's algorithmic, right? I have to build a bigger matrix, but some of that also has to do with the structure of how the computer itself handles representing that big matrix. Okay, so the memory inside your computer has a natural hierarchy associated with it. So in your CPU, so that's the thing that's actually implementing the little bitwise operations like multiplying two floats, et cetera, et cetera. That CPU needs memory to do that, right? Because that memory is going to be what tells it what to do. So the program instructions are in it, but it's also going to be what stores the individual variables that get used in those computations. So the memory that your CPU can most easily access are the registers, which are usually on the scale of tens of bits. And the registers usually contain things like program instructions, and maybe they contain some data, but I think typically they don't. And so this is relatively small amount of information. This is just going to be basically enough to specify that I'm doing a product or whatever on a single sort of CPU cycle. So then the most important thing for the scaling complexity, especially on something small like a laptop, is going to be the size of the L1 and L2 caches. So these are going to be elements of the memory that are relatively close to the CPU. One of them is implicitly inside the CPU, and one is just like one step removed. And so these store data that can be moved in and out of the CPU relatively quickly. So these are hardware level details, and so there is a limitation on how much memory these can have. Currently, the L1 cache is on the order of tens of kilobytes, and the L2 cache is on the order of hundreds of kilobytes. I believe that's still accurate as of when I'm recording this. So what that means is that that's about as much information as the CPU can see at a given time as it performs an operation. So what that means is that if I'm doing some really crazy operation that involves adding a bunch of numbers or doing a bunch of sort of a calculation that involves a lot of different data points, so a lot of separate floats, I want to try to keep as many numbers as possible within the size of the L1 and L2 caches. The reason for that is because this is the memory that's the easiest to access. Once I get beyond the size of the caches, I end up in this limit where now I have to store data in main memory, and getting data out of main memory is slower than getting it out of the caches. So what that means is that the bigger the amount of data I'm performing operations on, I can hit basically a step threshold where the moment it takes enough memory that I have to store things externally, I can get a really big slowdown because I constantly have to shuffle data in and out of memory and into the caches. So this is a hardware level detail that can affect the observed speed because once you hit the limit where you're transferring things from main memory to the caches, then you can run into trouble. And I'll just mention that people talk about the memory hierarchy to arbitrary levels of detail. So beyond your main memory, you've probably encountered before the problem of swap on your laptop. So if you have a program that requires more than your amount of RAM, then sometimes it will try to put some data on your hard disk and then like shuffle data between your RAM and the hard disk as needed. This hasn't been a problem as much recently, but for those of us who grew up with really old computers that had 1 gigabyte of RAM, hitting swap was a pretty common issue, especially because back then your main memory would be a spinning disk, which was much slower than flash memory. And so that's like a grown up version of this L2 cache problem, where it's the same issue, which is that your memory needs increased to the point where your actual mode of where you stored it changed, and accessing that slower mode ends up costing a lot more time, right? So swap memory is much, much slower than accessing RAM, to the same way that accessing a RAM instead of the L2 cache was a lot slower. And then you could take that idea even further and say, oh, sometimes things are too big for my laptop, so I'm going to try to store it on like my local area network. So now I have latency induced by pulling the data off my local server. And then there's always the worst case scenario, which is that I'm dealing with data that's so big that I have to download it from some remote like internet repository. And so that's super slow. And so I really don't want to have a computation that requires me to constantly fetch my latest set of floating point numbers from some server somewhere in Helsinki, because that's going to introduce sort of a relativistic latency that can't be avoided in the speed at which I could actually operate on those floats. So in other words, the memory hierarchy says that as you get to more and more memory requirements, the amount of time that it takes to access that memory increases as these steps, as I change the actual hardware that stores the data I'm trying to access. So why is this relevant to numerical integration? So here, the amount of memory that I use is going to be proportional to the size of the n by n matrix of phase differences. See, here I'm doing a timing test where I'm just going to test to see how long matrix multiplication takes on my computer as a function of the size of that matrix. So, there's a few details with how I've implemented this, but basically I'm just like, I'm doing 2 by 2 multiplication, 3 by 3, all the way up to 400 by 400 matrix multiplication. And I'm just timing to see how long my laptop takes to perform those multiplications. So when I look at my timing results, you can see pretty cleanly that I get some scaling, right? The problem's getting harder as the problem gets larger. Matrix multiplication is naively n cubed operations. It can be shaved down a little bit, but that's at least the schoolyard approach. It takes n cubed operations. So we should expect this to maybe be a cubic or subcubic scaling. But while that might be true algorithmically, in practice on my laptop, once we hit about 30, it looks like that's about 32 kilobytes, I get a big step in my runtime. So it gets way slower around 32. So what's happening at 32 kilobytes? Well, if I look at my hierarchy here, that looks like that's just about the size of the L1 to L2 cache transition. So it looks like I hit this limit where now my CPU is having to fetch data from this slightly less fast cache that's outside of the CPU itself. So that introduces latency that shows up as a spike. So I can literally see the hardware of my computer manifest in my timing results. And then I keep increasing, and it's kind of spiky because there's all sorts of weird stuff that happens depending on where the data is stored and how amenable it is to the matrix multiplication. So this step here is a hardware result. So the actual scaling here might still be n cubed or slightly just under n cubed, but I get this big increase in the prefactor due to hitting the L2 cache. Okay, so I can keep up with that. I can increase my array size. So now this axis is in megabytes rather than kilobytes. I still see this power law trend, maybe something weird here. I wasn't able to hit the other levels of this hierarchy, partly just because of limitations on the amount of time I could run this notebook before running out of memory or having like it crash. But you could imagine if I could run this matrix multiplication up to arbitrarily large matrices, I would see additional steps appear here where I got the moment I switched the mode of memory I'm accessing, I would see a big jump in the prefactor associated with the matrix multiplication runtime. So what does that mean? That means that I could see slowdowns in numerical integration that are step functions with the number of dynamical variables. So in my oscillator example, that's the number of oscillators I'm keeping track of. I could see a nonlinear change uh, in the runtime associated with numbers of oscillators due to just hardware restrictions. So importantly, I can't get around the way I calculate this, right? This is very different than what we did at the beginning of class where we talked about algorithmic ways to speed this up. This is all sort of a hardware effect. And so we're going to try to find ways to mitigate the hardware effect here. Okay. So those are my timing results and they depend on hardware. Okay, so the first thing that I could do is I could maybe shave some time off by using a larger time step with an implicit solver. Okay, so instead of calling, so the idea here is I can speed up my process by instead of having to, if I want to integrate for 100 time steps, I could increase my time step, but use a solution method that's stable for larger time steps. So this wouldn't work if I just increase my time step without any sort of control, because as we saw, if I increase my time step in a fixed step integrator, I can run into problems. But if I have something like an implicit method that tries to make a step and do the solution method, I can get stability back even at a larger time step. So I can use an implicit method. So doing that requires me to analytically define the Jacobian of the Kuromoto oscillator system. So I have n oscillators, so I need to define an n by n matrix that tells me how much the instantaneous change in a given oscillator's phase depends on every other oscillator. So that's a relatively simple matrix to define for the Kuromoto model. It's just the derivative of that right-hand side that we saw. And so if you write it down, it ends up looking like this. You get a cosine term, right, because you're taking derivative with respect to phases. You get a diagonal term, and then you also will find yourself with the same Kuromoto prefactor appearing. So again, you can do this analytically. It requires a bit of work. You don't want to try to do this using finite differences because as n increases, the cost of doing finite differences increases as I believe n squared because you have to check every direction. So it's good to be able to do this analytically. And it just so happens that the Kuromoto model has a relatively simple form of its Jacobian. So I give this explicit Jacobian function. I'm going to overwrite my existing right-hand side model just to add the Jacobian. So now I have this augmented model that has the existing Kuromoto plus the Jacobian. And then I'm just going to pass my solver the Jacobian as an argument. So solve IVP, as well as whatever your favorite package is, usually has a keyword that takes the Jacobian as an argument. So I pass this Jacobian function as an argument to Jack. And then that allows this implicit step integrator to use that Jacobian without having to use finite differences. Okay, so that's a lot, but the idea is that I just define an analytic Jacobian, pass it as a function to my integrator, and then that can be used for implicit methods. Okay, so I pass that, I run my Kuromoto model, I get the same results as before, so I haven't broken anything yet. So in principle, we'll see if this helps with our speed at all. Okay. So here I'm going to run the Kuromoto model. So we'll start with this bottom line here. Here I run the Kuromoto model in the absence of having an explicit Jacobian, and I get a pretty good runtime. But then if I actually add the Jacobian in, you'll notice that I actually run into a much larger time, right? So I actually increase my runtime. So the reason for that is because right now I haven't actually done anything to change the number of evaluations. And so adding the Jacobian just to the implicit solver always will give you an overhead cost because the Jacobian requires a bunch of evaluations to fix those matrix elements. So what that means is that adding the Jacobian always increases the number of operations that you do per call to the right-hand side. But our hope is that the stability that the Jacobian provides to the implicit solver might allow us to use fewer time steps to compensate for this hit that we take in order to use an analytic Jacobian. Okay, so because it's going to be a bit slow to integrate, I won't run this. But basically, if you don't change your time step, implicit methods are slower. And if you pass the Jacobian, it takes more evaluations. But I might be able to get away with adding a smaller min step argument. And so I might be able to, if the default is maybe something like 1 e to the minus 3, I might be able to do something like that and take way bigger steps to reduce the number of calls uh, at the expense of having to evaluate this Jacobian at every iteration. Okay, so the Jacobian basically can allow you to use fewer time steps, but it will always cost you more than not using a Jacobian with a fixed step method. So that's one optimization I could try to play with to make this problem a little bit better behaved. However, another method, and this might be more generally useful because sometimes finding the Jacobian is a little bit difficult, a slightly more general method is that I can basically say, I have some right-hand side, it's difficult, it's painful to work with, I don't want to find the Jacobian or try to play with my integrator. Maybe I can squeeze speed out of the problem by just-in-time compiling just that right-hand side function. So basically, I can try to say, instead of having Python try to figure out, oh, I'm taking this matrix of floats and creating this new matrix and then contracting and spitting out a vector, I could maybe try to compile that so that the types have already been inferred, the size of that matrix is already known. And so now I can do this super fast because I have some compiled representation of the actual Kermoto update step. So we don't want to compile the whole integration routine. We just want to compile the step that we call every integration time step. Every time we call the right-hand side, we want to hit a compiled function. Okay, so that's the ambition here. So we're going to use here a method in Python, or a tool in Python called Numba. This is basically a package that implements just-in-time compilation. There are other packages that do that. I'm just using this as an example because it's suitably easy to use. But importantly, this is not a technique. This is just an implementation of a technique. So the idea is that Numba is a package that is pretty well designed to be able to take raw Python code, infer the types, infer the computation graph, and compile it. It compiles it using this method where it basically takes the Python code, it runs it through this method that finds what are called intermediate representations. And then it takes those intermediate representations and it compiles them to what's called machine code. So this is the code that your computer can understand. And what's interesting about this is that these intermediate representations are language agnostic. So for example, a Python representation of, let's say, the Fibonacci function would get compiled to similar intermediate representations as, say, a Java implementation. So this intermediate representations is like sort of like a universal language that's intermediate before we go to the machine code. So what Numba basically tries to do is it tries to look at the Python program that you've given it, figure out these intermediate representations and how they string together. Then it translates it to bytecode, which you can then use to speed up your integration in future calls to your function. That's the basic set of operations here. So in practice, the actual sort of sequence of operations that Numba will do is I'm going to give it my function. So here in this little diagram is this calc function. It's going to first look at the arguments and try to infer the types. It's then going to look at the actual sequence of computations and try to sort of structure it into these intermediate representations. Those two things it's going to put together to write this intermediate representation that represents the entire program. Then it spits that out into machine code. And the first time I run this function, it's going to actually create the cache. So it's going to actually do the compilation. And then on all future calls to calc, it's going to use this compiled version. And so the first time might take a little bit, but the subsequent calls should be super fast. That's at least the hope behind this. And the way Numba actually flags a function is going to be relatively easy, which is that if I have Numba active in my environment, I can basically put a decorator on the function that tells Numba to try to do this caching and compilation of the function. Okay, so Numba is pretty easy to use. Basically, if you're lucky, you just import Numba, you import this decorator, you take whatever function is giving you trouble, and then you just run this Numba thing, and you'll get the compiled version without having to write any code yourself or write any compilation code. In principle, when this works, it works really, really well. And so Numba can compile individual functions to speeds that are basically comparable with native C or C++ code, which is actually really cool because even if you don't know C or C++, you can access that speed at least at the level of individual functions if you run this number operation on them. As a library, it's pretty good at recognizing when you're working with arrays. So it usually won't throw errors if you're doing basic array arithmetic because it knows that people use arrays a lot. So the designers of Numba have come up with all the different cases. And importantly, Numba is nice because I can use it within my Python environment. So I don't actually have to go and write separate C code that my Python code calls. Instead, I just can decorate my existing code and have the super fast version without even having to know anything about C. Having said that, there are some drawbacks, which is that there are certain operations that Numba cannot do due to the nature of what Python can do versus what compiled languages can do. There are certain abstractions that exist in Python that don't have a clean representation in the intermediate representations. Sometimes with things like slicing or reshaping arrays, you'll run into bugs with Numba, which can be a bit difficult to interpret. So when Numba breaks, it can be a bit difficult to troubleshoot, and there are in fact some operations that might not be possible to just-in-time compile. Okay, so Numba can't do everything Python can do. I can't just take my entire Python code and say compile at Numba. I have to be pretty surgical where I take single functions that do well-defined things and I compile those individually, and then I glue them together with Python. The other thing that can get annoying with Numba, and this is just a matter of preference, but in my experience, it can be a little bit hard to install Numba, especially on weird hardware. So for example, I'm doing this on a Mac. On a Mac right now, Numba is working, but you should probably install Numba using Conda rather than pip, because in my experience, Conda is better about managing the dependencies to get the whole compiler working. And the reason it's difficult to install has nothing to do with the design of Numba. It really is because those of you who work with compiled languages are probably used to fighting with things like CMake or other compilers. There's just a lot of things you have to worry about with the match between your compiler version, your hardware version, et cetera, et cetera. And because Numba on some level is a compiler, you're going to hit all of those weird bugs when you try to install Numba on your computer because it has to figure out your hardware configuration. So that can be a little bit painful, and that's just the downsides of working with compiled languages. I've had some issues on the cluster with Numba because on the cluster you have different hardware configurations. So this is just something to be aware of, which is that getting Numba running can be its own odyssey depending on your configuration. Okay, so that's Numba. That's basically how it works. Yeah, and there are other JIT compilers for Python that I won't get into, but I'll mention that on some level they're all doing this basic graph. Okay, so what does it actually look like to use Numba? So here I have my Kuramoto model. I'm going to basically just subclass it to add the compiled method. This is just going to be so I don't have to rewrite all of my initialization code. And I mentioned that you have to use Numba surgically, so I can't go in and compile this entire class. So instead, I'm going to define a special function that's going to be what actually gets compiled by Numba. So Numba, I import this decorator called ngjet. That stands for no Python just-in-time compilation. And then I pick that function and I run this decorator on it, and that tells Numba the first time that this function is run that it needs to try to compile this. And you'll recognize that this is the same logic as before. It implements the right-hand side of my Kuramoto model. So I've taken that core code, that core operation that I do tons and tons of times. I've written it in its own function and I've compiled it. So you can see from the way I've written this that there are two drawbacks to Numba that you have to sometimes deal with. One of them is that Numba generally prefers when all of your arguments are individual parameters that are one of Python's native types. So Numba doesn't generally like it if you give it keyword arguments because it doesn't really know what to do with those. And so usually it's going to be better behaved if you don't actually have these as keyword arguments. You just unwrap them to just traditional arguments. So you can just treat this like a function that's guaranteed to always get 5 values passed to it. So in order to define this function as compiled, you can see I actually wrapped that function with this sort of like helper function that takes the keyword arguments and feeds them to this. So that's a little bit janky, but that's just a way to get around limitations with how Numba can handle this. The other thing that you'll notice is that there's no self argument here. So basically, I've kind of hacked this to avoid this function depending on self. The reason for that is because self is a Kuromoto model data type, right? It's some abstract object that I've defined, which Numba will have no idea what to do with. So here I'm going to use this trick we saw earlier in the class called a static method. I think we saw this in the first or second lecture. This is basically a way to define a function that's bound to a class, but which doesn't depend on self. That's all that this means. And so this is just going to be a way to sort of flag this as a special function that doesn't have to take self. And now I'm able to have this function that just takes explicit arguments with no weird abstract types, right? Because basically RHS underscore RHS takes a bunch of floats and gives me out a bunch of values. But the painful thing here is because of the limitations of what you can compile, I had to have this wrapper that actually puts things in this nice format so that the compiled function can see it. So I am going to pay a little bit of a penalty for this overhead, but the hope is that the savings of this compiled version are going to compensate for that overhead, as well as overcome the downside of having this slightly less intuitive code to read. Okay, so actually using Numba was just a function of adding a decorator. I just had to make sure that my function that takes that decorator didn't have weird data types or keyword arguments. Okay, so that's my just-in-time compiled Kuromoto model, where the compiled portion is just the call to the right-hand side. So here I'm going to use that. I'm going to solve this problem again. You can see I get dynamics that look correct. So my logic hasn't changed. My solution stays the same. So here I'm going to do a timing comparison. So you can see that here I took my original Kuromoto model, I ran it, I got sort of a certain runtime. But then if I use my Numba model, I actually get slightly lower time here. So you can see I got a pretty noticeable drop off. And I also got a noticeably lower variation across different calls. So a couple of things to unpack here. One of them is that I got a relatively modest difference here, right? I got about 30 milliseconds. But as I increase n or I increase the number of evaluations, the amount of time I expect to save, I would expect to increase linearly with the number of calls. So if I decide I want to integrate this for 20,000 instead of 10,000, I can expect to see my difference increase by a factor. I'd expect the difference between this and this to double, because the advantage I'm getting compiling the right-hand side is played out across more calls to the right-hand side. Okay, so Numba sped up my right-hand side by compiling it. The reason that this isn't much faster or dramatically fast is because unfortunately for this problem, I had to do this wrapper, so I still have to call this kind of inefficient function to get to Numba. But you can imagine that there might be ways to refactor this entire problem where I get more of the core loop to stay within Numba, and that might allow me to get even more dramatic speed ups from compiling the right-hand side. One detail is you'll notice that here I initialized the model and then I did a call to the right-hand side before I ran the timing test. That's because the first time I call that right-hand side function, that's when Numba runs this loop where it does the compilation and caching. So here I have to, or catching, I guess. And so here I have to do that explicitly first so that that's not caught up within this loop. So basically this forces Numba to do the compilation early because it runs the computation graph. And then after that, this function should have the compiled version. Okay, so that's Numba. That was a lot of detail, but the basic takeaway there is that I take the right-hand side that I want to speed up. I surgically apply Numba. I might have to make some changes and refactor my function to get it to work with Numba, but then this should be compiled, and so then that should run super fast. But I do it surgically just for the part that I want to be fast. Here's my call to my right-hand side. Okay, so that's Numba. I use Numba a lot, but I should mention that there are other ways of doing this faster. So I won't get as much into this, but I'll mention that there's another option called Cython, which is a language that tries to superset Python to include C-like data types. So here's some example of some code for integration. This is someone else's code where it shows you what the difference is between the pure Python version and the Cython version. And you can see that basically the Cython version looks pretty similar, with the big difference being that you have explicit type declarations, right? So in Python, you have doubles, you have ints, and you actually explicitly define variables as belonging to certain types. And so what Python code looks like is Python code always is a .pyx file. And Python takes this code, which looks like kind of like a blend between Python and C code. It has hopefully some of the brevity of Python with the explicit type declaration of C code. And then this .pyx file, you actually will explicitly compile before you do anything. So rather than implicitly doing a just-in-time compilation, Python is actually a compiled language that looks like Python. And so Python is interesting because if I have something that I can't write in the Python form, I can write just pure Python functions into a .pyx file. They just won't get any of the speed benefit of explicit type declarations. So Python is another way of doing it if you want to actually explicitly compile something. You have to deal with all the same kinds of concerns that you might run into when you do explicit compilation with C or C++, but it might be able to solve issues that Numba can't if you're having trouble fighting with Numba to get it to compile parts of your code. So, Python is a nice intermediate between Python and going full C++. I'll just mention that some of the downsides of Python is that it's a little bit difficult to install because you have to get your Python installation, your Python compiler, and your C compiler to all work together. So you have some hardware dependencies. It has this issue of being intermediate between Python and C. So its readability is not quite as clean as Python, but not quite as difficult as C. You get more lines of code you have to read through. It's not as easy to use as Numba because Numba, in the best case scenario, you just decorate a function, now it's compiled. Whereas with Python, you have to write special .pyx files and compile them. A lot of methods that you might want to use, like NumPy is okay, but some of the more exotic external packages in Python don't necessarily support Python, which means that the number of imports you can have in a .pyx file isn't arbitrary. For example, I can't just import scikit-learn into a .pyx file. So generally, you have to isolate these files to just include very basic logical operations and not too much of your code's more sophisticated portions that depend on external packages because Python doesn't know what to do with those external dependencies. So then, in this last bit, this is just my opinion. And from what I can see, Python is declining in popularity due to the rise of things like Numba, as well as some of the more machine learning friendly languages like JAX or PyTorch, which are very, very highly optimized. So Python, I don't see as much new code being written in it. And so I hesitate to recommend it as a first approach because it has this issue of why wouldn't you just use C in the first place if you're going to use Python? Because at least then there's a lot more resources for working with C and C++ code. But again, that's just sort of my opinion. That's not necessarily a survey of what the field would say. So if I were running into something where I needed more speed, I would probably try Numba first, or I might try another method like JAX, which we'll see downstream, or Julia, before I try to use Python to speed up integration. Okay, so then the last thing I want to talk about is something that's just starting to emerge as a really big language in scientific computing. This is something I'm pretty excited about. So this is a new Python library called JAX. That basically is an extremely optimized linear algebra library. So basically all of these matrix multiplications or vector operations that we find ourselves doing in scientific computing, this is in principle a very, very efficient way of doing them. Okay, so JAX, there's a lot going on under the hood. I'm not an expert in this area, but the basic idea is that it has some of the speed you get of just-in-time compilation combined with sort of low-level primitives that are very, very friendly to working with arrays. It's backed by a major company. It's developed in-house by Google, so there's a lot of support behind it. And it has, as we'll see below, it has the ability to perform automatic differentiation natively, which is extremely cool and extremely useful for certain types of problems. Okay, so JAX is basically it's an alternative linear algebra framework that has some optimizations that are borrowed from older solutions like Numba or other methods. Okay, so basically the simplest way that you can imagine using JAX is that JAX as a library includes within it basically an optimized version of NumPy. So here what I'm going to do is I'm going to import JAX's NumPy clone as JNP. So NP functions are NumPy. So JNP are going to be things I'm replacing with the JAX equivalent. And then I'm just going to take my Kuramoto model and I'm going to overwrite, right? So it inherits, but this right-hand side is defined later, so it overwrites. I'm going to overwrite the right-hand side with basically the same code as before. I'm just replacing NP by JNP, right? So it just tells it to use JAX's version of NumPy rather than the original NumPy. Um, so that's really easy and really simple to do. I don't have to worry about rewriting functions. And so it's remarkable that this would give me any advantage at all, but it turns out that it actually gives me a really noticeable speed up on this problem. So here, this is my original Kuramoto model. It takes a bit of time, but just adding basically J and P in two places halved the time, which I think is just remarkable. Okay, so that's pretty good. But I should mention that I'm just sort of showing the basic way you could get a speed up here, because there's still a lot of things in my code that I haven't optimized. For example, solve IVP doesn't know about JAX. So every time it gets an array from the output of this right-hand side, it actually has to cast that array from a JAX NumPy array to a normal NumPy array. It then does operations, then shuffles them back, and then JAX implicitly has to do the inverse of that operation. So there's a lot of like switching back and forth between NumPy and JAX. And so there are even solvers people are making that keep the entire sequence of operations purely within the JAX NumPy environment or the JAX environment. And so those end up giving you much bigger speedups than just this factor of two. So you can get really, really dramatic increases in speed just by keeping as much as possible within JAX and trying to avoid round tripping through NumPy. So JAX is really cool. It's really easy to use, especially as someone coming from NumPy. And it has a lot of things going on under the hood that make it a really kind of natural choice for speeding up scientific computing problems. So I really recommend it for projects or for just playing around with because of how dramatically well it works, especially if you're used to Python. I will mention that, like Numba, there are certain things you can't do in jax.numpy that you can do in full NumPy. They're trying to support as much of the original NumPy library as possible, but there are some things that are just intrinsically difficult to cast into the XLA representation. So it's not quite equivalent. So you might run into cases where you can do something, but if you swap out JAX and NumPy, it doesn't work anymore. But in my experience, the number of things that you run into an issue with is relatively small. So I really recommend JAX. I find it really powerful and surprisingly easy to use. Okay, so JAX is really cool. One of the things that it does, in addition to having all these hardware optimizations, JAX is also super fast. Or sorry, JAX, in addition to being super fast, JAX also supports a lot of other things that aren't present in vanilla NumPy. So I'll talk about this more in class. I won't talk about it too much now, but if you want to check out this notebook, you can see what I'm doing here. But the basic idea is that most numerical linear algebra operations I perform in scientific computing, I might have something like a vector that I raise to a power. Maybe I take sine or cosine. Maybe I add vectors. The number of actual things that I do inside a function like this is relatively small. And so JAX includes this built-in support for taking the derivative of the output of some sequence of operations with respect to the input. So if I have some vector, I pass it to a function, I get some output, JAX will at the same time figure out the computation graph needed to take the output and find the gradient of the output with respect to the input. So it basically has native support for the ability to take derivatives of arbitrary linear algebra functions, which I think is really cool. So I probably won't do this today because I'm running a little bit short on time, but I'll just mention if you want to look at this, the way that you do automatic differentiation is pretty cool, which is you take your basic computation, you write it down as a series of primitive operations, and you can basically write the gradient of any primitive set of operations in reverse as a series of primitive chain rule operations. So JAX basically figures out this computation graph where you perform a series of basic operations to get your output. It stores that graph and it maybe stores values of input-output pairs. And then when I ask for a derivative, it traverses that graph backwards and figures out how to accumulate these node-wise derivatives to build up a chain rule that gives you output with respect to input. And you can play around with this a little bit, but I'll talk about this a little bit more when we get to the machine learning part of the class. So JAX is not just cool because it's very optimized for linear algebra. It actually, some would argue, is a new way of thinking about scientific computing because it has built-in support for automatic differentiation. Okay, so I really like JAX. I recommend it, especially for this class where we're using Python. So just to conclude, I'll mention that a lot of new scientific computing work is being done in Julia, which is a new language distinct from Python that tries to fix some of the little peculiarities of Python as a language, while also introducing a few nice things like just-in-time compilation built in, et cetera, et cetera. So I'm not a Julia expert. I'll just mention that from what I can tell, Julia is exploding in popularity, especially within scientific computing. A lot of the things we've seen in this notebook, like automatic differentiation, just-in-time compilation, a lot of that stuff is either built in or very easy to add to Julia. And Julia has this feature where, because it has just-in-time compilation built in natively, you don't have to worry about fighting with Numba to get it to work. And it has native speeds that can rival even some very good compiled languages. So Julia, because it's a new language, it can learn from some of the advancements in the past 15 years and get around and do a lot of these things very, very efficiently. So Julia is a very nice language. It's very nice for scientific computing. I will say that it's not quite used widely outside of scientific computing. That might change over time just because oftentimes languages start out being used by academics and then they sort of grow outwards from there. But I'll say that, if I had to guess, I imagine we'll see Julia grow in popularity because I compare where Julia is now to where Python was relative to MATLAB when I was younger, where a lot of people told me not to use Python because it wasn't mature enough, there wasn't enough support. And now here we are 10-ish years later, and Python is extremely powerful. And I imagine Julia is similar, where Julia has a lot of advantages over Python. It just has to build support. So, if you really want to look to the future, I think Julia is a very interesting language to explore. And I think that there's a lot of details to how it operates under the hood beyond what I've discussed here that suggest it has a lot of advantages. Okay, so I'll go ahead and wrap up there. Hopefully that gives you some idea if you're just given some weird differential equation, either in the context of your project or in just your research, of what some tricks might be to make it work faster. Thank you.